All right, yesterday we were looking at synthetic division, and we left off yesterday with this remainder theorem concept. We're working on page 131. I don't believe we finished these. I think we were on number 3. Is that right? Yes? Okay. So let's just have like a little refresher from yesterday. Synthetic division went really well. We're going to do a few more of those today. But what about the remainder theorem? Can someone kind of describe that for us? What did we see yesterday when we went through some examples? There was some type of pattern or relationship between synthetic division and a function value. Maybe look on page 130 to refresh your memory. Yeah. Okay, so something we talked about yesterday, if there's no remainder, aka remainder of 0, then the divisor is a factor. It goes in evenly. We're going to see a little bit more of that today. Okay, when we take a look at the factor theorem, something new. What about the remainder theorem? What did we notice yesterday? Good, Alex? Yeah. Say it again. If it
said x minus 2,
yeah.
Your remainder would be 2.
Not necessarily. It is something about the divisor, though. We gotta look there for something. Yeah, Hunter? The remainder is the same as the function value, meaning if we plug something in, the number we get out is representing the remainder. Okay, so what number are we specifically plugging in, though? Yeah, the 0 of the divisor. Okay, so take a look at number 3. For what value of k will that function have a remainder of 0, meaning it goes in evenly, okay, when we divide by x plus 1? So what's the 0 of that divisor, x plus 1? Negative 1, okay? So if we were to plug in negative 1 for all of those x's, our answer would represent the remainder if we were to go through the synthetic division process. Not that we have to do it, okay, but it should represent the remainder. And in this case, for number 3, we want a remainder of 0. So that means we should be able to figure out what this missing k value is. What's this missing coefficient in the equation? So doing a little solving. Looks like our missing coefficient's -9. Okay, that's something we saw from yesterday, and we're going to be using that remainder theorem concept a little bit more today. If you were to plug in the 0 of the divisor into the polynomial, okay, your answer is representing the remainder. Okay, what's left over. And this is going to be really easy for us to do because we're essentially just plugging in a number and we're seeing what we get out. Okay, whatever we get out is representing a remainder. Eventually, like Helen said, we're going to be looking at remainders of 0 because we know those are special. They go in evenly. Okay, they're factors. So if we get 0 as an answer, okay, like this one was, remainder of 0, we know it's a factor. It goes in evenly. Yesterday, we utilized a calculator for some problems, and we're going to need it again today. So if you have one of your own, you can go ahead and get it out. Maybe you want to go ahead and grab one of my yellow ones. We're not going to need it for every problem, just here and there. And we're not going to graph anything, so if you have just a standard calculator, you could use that too. By the way, where are my volleyball players? Over here. Good luck tonight. I'm going. Yeah. My husband teaches at Red Bank, so it's a conflict of interest. We will be sitting on opposite sides. Okay? All right, let's take a look at number 4. Suppose that function g of x, okay, polynomial, we have x's to powers, is divided by x minus 1. Or sorry, x minus 2. Which is greater? Okay, so we kind of have to figure out two things here and then compare them. We're going to first try to figure out the value of g of negative 2, and then we're going to try to figure out the remainder if we were to divide g by the x minus 2 divisor. Okay, so we got to figure out two things. Let's go ahead and tackle the first one. G of negative 2, what does that mean? What does that tell us? What's it asking us to do? The x value is negative 2, so we're going to plug in negative 2 for all those x's. Let's see, some of you might be able to do this kind of fairly quickly in your head. Maybe you got to utilize a calculator for some bigger values. Plus 16 minus 6 minus 2. 28 minus 8, we got 20. All right, so the value of g of negative 2 is 20. We're going to have to compare that to this other value, which is going to be the remainder when we divide g by x minus 2. How do you want to figure out that value? You kind of have two options you can do. How do you want to figure out a remainder? We could go through the division process, okay? Which number in the synthetic division process, by the way, represents the remainder? The what? The bottom right one, or the very last number at the bottom of the setup, okay? So we could go through the actual division process, or what if we utilize the remainder theorem? Okay, what would that look like? If our divisor is x minus 2, what number would we have to plug into the equation? 2, okay? Do we have a preference? Do we want to try both just to see we get the same result either way? You want to do the remainder theorem? Okay, so we're going to take the 0 of the divisor, which is 2, and we're going to plug it into the polynomial. In other words, we're going to try to calculate g of 2. So very similar to the last one, we're just going to plug in positive 2 instead of negative 2. Does 0 sound about right?
Yep.
Double check my work. Yeah? Okay, so this 0 is your remainder, okay, if you were to actually go through the division process with x minus 2, okay? So now that we know both values, which one's greater? We have 20, we got 0. Clearly we know 20 is greater. Okay, so kind of big idea from yesterday with the remainder theorem. If you took the 0 of the divisor, plugged it into the polynomial, Your answer is representing the remainder, the leftover stuff. We're going to see a little bit more of that today show up. Okay? We're going to transition to kind of our next big theorem from this section called the factor theorem. But it's nothing really new to us. Helen kind of mentioned it earlier. If somehow we get a remainder of 0, we know that the divisor is a factor. It goes in evenly because nothing's left over. So we're going to kind of take a look at some connections here between a factored equation, a standard form equation, what the graph looks like. Okay, all three of these representations are the same idea. This factored form and standard form are the exact same equation, they just look different. So factored form is when you have your little groupings, okay, all being multiplied together. But if you were to actually go through the multiplication process, like FOIL, distribution, get rid of all the parentheses, you would end up with your standard form equation. So these are exactly the same. One's just simplified without the parentheses. And if you were to graph either one of these, this is what it would look like on a graphing calculator. Okay, so all three of these represent the same function, whether if it's factored form, standard form, or a graph. What we're going to do is, based off the graph or the factors, we're going to identify the zeros, okay, x-intercepts, and we're going to use those x-intercepts as our little box numbers in synthetic division. Okay, we're going to see what happens if we go through that. So either based off the factors or the graph, can we identify some x-intercepts? Yeah. -2, 1, and -1. Okay, so -2, -1, and 1 based off the graph. If you look at the factors, we would have -2, 1, and -1. Okay, remember the factor or the zeros come from the factored form if you were to set it equal to 0. Okay, so we're going to let these zeros be our little box numbers in synthetic division, however setup you want to use, because we looked at 2 different kinds yesterday. And we're going to go ahead and utilize the coefficients from the standard form equation, making sure they're in order and using any 0 placeholders if necessary to go through synthetic division. So in this case, it doesn't look like we need any placeholders. We'll just write down the coefficients. Do we need a refresher on synthetic division, or are we good from yesterday? Refresher? Okay. We drop the first number. Take your box number times the number you drop down, which in this case would be -2, and you place that underneath the next coefficient. Then what do? Add them together, right? So 2 plus -2 actually gives us 0, and we're going to repeat the process. Box number times new bottom number would be 0. Add with the other coefficient, which would be -1. Repeat the process. All right, and we're done with synthetic division. All right, so that's what we would get. Okay, this is our synthetic division setup if we were to divide the standard form equation by the x plus 2 factor, because notice how -2 was the little box number. Okay, this is our result from that factor. We're going to check out what the other results would be. What if we were to divide the standard form by x minus 1? What if we were to divide it by x plus 1? Maybe there's some type of pattern going on here. So this other x-intercept of 1, let's do a synthetic division for that x-intercept. We're still going to have the same coefficients because it's still the same standard form equation. All right, so that would be the synthetic division if we were to divide the standard form by the x minus 1 factor. Notice how it's a little different from the x plus 2. Okay, let's go ahead and try the last factor, or 0 of -1. kind of running out of room. We'll have to write small. All right, so after we took the time to divide the standard form equation by all three of its factors, what do you notice about those synthetic division results? They all have a remainder of 0. And shouldn't that kind of make sense to us? If these are the factors, doesn't the word factor mean divide in evenly, aka remainder of 0? Right? 2 is a factor of 8. 2 goes into 8 evenly. Okay, there's nothing left over. So it makes sense when we go through the process we should get a remainder of 0. Let's see if that kind of holds for the other two examples. Okay, so looking at the factored form and the standard form and the graph, let's go ahead and identify some zeros. Okay, x-intercepts. You can either look at the graph to help you out, you can look at the factors to help you out. Based off the graph, though, it only looks like we should have 2. Can we identify those locations? Yeah? All right, negative 3 over 2. Okay, that's probably coming from the factor, but that's the same as negative 1.5. Okay, notice how that's showing up on the graph. And the other one looks like a positive 1. Okay, so we're going to take the time to synthetically divide these zeros, these x-intercepts, by the standard form equation. We still getting those remainder of zeros? We doing okay? All right, let's try the next one. There was a little typo type thing on this one. You see the number 1 on the left-hand side? Okay, that should really be minus 1 at the end of that polynomial. For some reason, it kind of moved it. So go ahead and make sure you write it there so you don't lose it. All right, so either based off the factors or the graph, where are some x-intercepts? Looks like 1 is clearly an x-intercept based off the graph. What about the other one? Kind of iffy. Looks like negative 2.5. So maybe we'll go based off the factor. 2x plus 5, if you set that equal to 0, you'd have negative 5.5, which happens to be the same thing as negative 2.5. Okay? So let's go ahead and see if we were to take these factors and divide them into the polynomial, what would we get? We have decimal coefficients this time, but don't get too worried about those. It works the same way. Can we still do synthetic division with decimals? Did it work out for you on your calculator? Still doing okay? All right, so notice how we still get a remainder of 0. So there's something going on here, okay? We're going to try to formally write down the connection that's going on here. What we're noticing, hopefully, is that if you were to take a factor, okay, specifically representing an x-intercept, and divide it by your polynomial, okay, like all the synthetic divisions we were just doing, notice how the remainder is always 0. Okay, it's going to go in evenly every single time. So we'll say when a polynomial is divided by one of its factors, the remainder is always 0. All right, graphically speaking, we saw that these represent x-intercepts, okay, where we cross or touch the x-axis. So this is leading us into the factor theorem, okay, nothing new because hopefully it's kind of common sense. We mentioned it yesterday too. If you were to get a remainder of 0, it means the divisor goes in evenly, aka it's a factor. So we're going to take a look at that concept today. We're going to be focusing on remainders of 0. Okay, because then we know something's a factor. So let's think about in the general sense here. If A is a 0, meaning an x-intercept, what does the factor look like? Okay, you can make A whatever you want. You can make it 1, -4, 3, whatever. If that number is an x-intercept, okay, a 0, what does the factor look like? That little grouping or divisor. Can we think about it? Yeah? X minus A, okay? So, if that's a factor, aka that's representing an x-intercept, if we were to divide a polynomial by that factor, we know the remainder should be 0. It goes in evenly. Okay, x-intercepts produce factors, aka the remainder is 0. Goes in evenly. So let's use that concept for some of these questions. Is 2x plus 1 a factor of that polynomial? Okay, show and explain your work. So how might you want to test that? What should we be looking for, and how do you want to find it? How can we test if something's a factor? How can we determine if it goes in evenly or not? Yeah?
If you plug it in, it equals 0.
If we plug something in, it equals 0. So Matt's mentioning something kind of like the remainder theorem, okay? So you have options. You can either go through the synthetic division process like we did on the last examples and see if you get a remainder of 0. Some of you might be more comfortable with that. Or you can utilize the remainder theorem because we're specifically looking for a remainder of 0. Okay? What would be the 0 of that divisor? What would we try to plug in? -1/2. Okay, so maybe we'll try that. Let's plug in -1/2 and see what we get. Whatever we get, that's representing the remainder. Right, so you may have to use a calculator for this one because we're raising a fraction to some powers. What'd you guys get as your remainder? 0. Okay, so is 2x plus 1 a factor? Does it go in evenly? Yes. Okay, so yes, 2x plus 1 is a factor because the remainder is 0. So we showed the work, we explained the work. So far, so good. There is another question, though. What is the graphical interpretation of your result? Okay, so if this is a factor, what do we know about this special x location of -1/2? Yeah. It touches or crosses the x-axis, okay? It's an x-intercept. So we can say, so the x value of -1/2 is an x-intercept. All right, hopefully this makes sense, because if we plug in -1/2, that's an x value. Doesn't 0 represent a y value, an output? Okay, and if your y value is 0, you're on the x-axis. Okay, you're touching that line. Okay, hopefully that makes sense. Let's try the next one. Is x plus 2 a factor of that polynomial? Okay, so you could either go through synthetic division, if you like that process more, or you could use the remainder theorem by plugging in a number. Do we have a preference? You want to try synthetic? Okay, we did remainder theorem for the other one. Maybe we'll try synthetic for this one. If you prefer remainder theorem, though, you can do that. Okay, plug in -2 and see what you get. Okay, let's try synthetic. Hopefully we get the same thing. So make sure your coefficients are in order, using any 0 placeholders if necessary. Doesn't look like that's the case, though, for this one. Can we get -34? Yeah, did anybody do remainder theorem? Did you plug in -2? Did you get out the same thing?
Yeah.
Good, okay. So is x plus 2 a factor? Does it go in evenly? No. Okay, no. X plus 2, bless you, bless you. Going for 3? No. That's okay. All right, no, x plus 2 is not a factor because the remainder is -34, okay, not 0. So what does this mean about the graph? Okay, if you were to graph that polynomial, that kind of roller coaster shape, what's that telling us? What's going on at this -2 x location spot? Clearly we're not on the x-axis, right? Because our y value is 0. Where are we located if our y value is -34? A negative y value, where are you? Below the x-axis. Okay, so we can say, so at the x value of -2, the graph is below the x-axis. Alright, so far so good. So the factor theorem, we're always looking for a remainder of 0, aka it goes in evenly, aka the divisor is a factor. Okay, it's going to produce those x-intercept spots for you, okay, y values of 0. What's nice about the factor theorem is that if we can figure out where one x-intercept is, we can figure out where all of the other ones are as well. Okay, it's kind of pretty powerful stuff. If you can figure out where 1, 0 is, you can figure out the rest. So that's what we're kind of going to explore here. Okay, we're going to take this polynomial and divide it by x minus 3. Okay, we're actually going to do synthetic division, not the remainder theorem. So what would be our little box number? 3. Okay, so let's go ahead and do that. It looks like we will need a placeholder of 0 for this one. Notice how there's no x squared listed in that polynomial. All right, so go through the division process. Oop, I wrote down a 3, not a 1. What do we know about x minus 3 based off the division? Yeah. It's a factor. Notice how the remainder is 0. Okay, so x minus 3 is a factor. All right, so let's think about this. We know that 2 goes into 8 evenly, so 2 is a factor of 8. What's the related factor for 2 that would give you 8? Remember, factor means multiply? 4, right? And isn't 4 the result if you were to do 8 divided by 2? Okay? So notice how if this x minus 3 is a factor, the quotient should also be factors. Okay? So if 2 goes into 8 evenly, notice how 4 is also a factor. 4 is the quotient. So this quotient piece right here could take us a little bit further. Maybe we can figure out the other factors and therefore the other x-intercepts. So if these are your quotient coefficients, what would the quotient look like with the x's put back into it? Yeah? Plus 3x minus 4, okay? So not only does x minus 3 go in evenly, but so does this quotient. Just like 2 goes in evenly to 8, 4 goes in evenly into 8, okay? Can we factor that quotient further? Can you think of two numbers that multiply to -4, add to 3? Kind of fits the IAM profile.
4 and -1.
4 and -1, okay? So notice how if we can figure out one factor, okay, x minus 3 in this case, we can figure out the other ones by factoring the quotient a little bit further using those factoring techniques. Okay, let's try a different one. Okay, we're still going to use the same polynomial, but this time we'll divide by x minus 1. So our little box number would be +1. Based off of that synthetic division, what do we know about x minus 1? It's a factor. Notice how the remainder is 0. Okay, so if x minus 1 is a factor, that means we could take the quotient further by factoring as well, figure out some other x-intercepts. So utilizing this quotient, looks like we'd have x squared plus x minus 12. Factoring techniques. Two numbers that multiply -12 add to 1. +4, -3. Good. Good, good, good. All right, last but not least, we're going to divide by x plus 4. So little box number is -4. Based off of that synthetic division, we know x plus 4 is a factor. Okay, goes in evenly. So we should be able to take the quotient further as well. In this case, we have x squared minus 4x plus 3. Factoring techniques. I am in this case again. Multiply to 3, add to -4. -3 and -1. All right, so moral of the story here. We're using the same polynomial in every case, but notice how it doesn't matter which divisor we choose, okay, x minus 3, x minus 1, or x plus 4. Don't we produce the other two missing factors every single time? So it doesn't matter which factor you utilize first, okay, which 0 you utilize first. It'll always produce the remaining ones that are left. So based off of these results, if we can figure out what the factors are, we can then identify the zeros, okay, the x-intercepts of the graph. So for instance, in the first one, we said x minus 3 is a factor. What is the x-intercept from that factor? What is the 0 from that factor? 3, okay? After we figured out x minus 3 was a factor, we were able to take the quotient further into factors, which means we could figure out those x-intercepts. One of the factors was x plus 4, which would produce a 0 of -4, and the other factor was x minus 1, which would produce a x-intercept of +1. So graphically speaking, we know that we are on or going through the x-axis at those spots. So if we wanted to, we could finally represent the standard form equation at the top in terms of its factors. Okay? If we have 3 zeros, we have 3 factors. We would have x minus 3, x plus 4, and x minus 1. Okay, kind of the opposite values of those zeros. Okay, do we see how kind of it's all clicking together? Okay, synthetic division related to remainders, related to polynomials, related to x-intercepts. Okay, all these connections. We'll take a look at some more like kind of practice problems tomorrow. So far, so good, guys.